So how are we going to understand the phase behavior of these different materials? So we're going to start by doing something that might seem a little bit counterintuitive, which is that we're going to make the problem a little bit more complicated than it was before. So up until this point, we've talked about the behavior of phases as a function of temperature. That is, we've talked about what happens as you heat a material or cool a material and how it changes phases when you do that. But there's actually many other ways that you can change phases while cooking than just playing with temperature. And another natural knob to turn, which is what we're going to talk about now, is pressure. So you can actually cause the phase behavior of a material to change by changing a pressure. Now, what is pressure? So pressure, of course, is the effect of the gas that is around us that is squeezing on ourselves all the time. So we get so used to it we don't even feel it, but actually the pressure of the air around us is pretty high. It's called 1 atmosphere of pressure, and it's essentially a force that's squeezing on us all the time, that our bodies are squeezing out at. Now, you know from either experience or not that if you climb a very high mountain, the amount of air that is around you decreases, and so the air pressure decreases. If you go up to about 16,000 feet or so, then it turns out that the air pressure around you decreases by about a factor of 2. And that's just because there's less air around you that's pushing, that's trying to squeeze on you. Now, physically, we can actually quantify what pressure is with a little bit of an experiment. One can take a balloon, for example, which is filled with air, and the air that's in the balloon actually is pushing outwards on the air outside, which is squeezing inwards on the balloon, and both are exerting forces on each other. So pressure actually is a quantity which has the units of force per unit area. Force is a quantity that physicists measure in units called newtons. That's kilograms meters per second squared. That's the famous Newton's law, F equals ma. It's a mass times an acceleration. And a pressure is a force per unit area, or it would be a Newton per square meter if you're using those units. The pressure I already said is 1 atmosphere. That's the definition of the pressure at sea level. And it turns out that that's about 10 to the 5th newtons per square meter. Now, scientists, in order to not have to go around saying newtons per square meter, gave that quantity another name, and it's called pascals, after the philosopher Blaise Pascal. With that as an intro, so let me show you what the phase behavior of water looks like as a function of pressure. So here's the phase diagram that I showed you before. At 0 degrees Celsius, water transitions from a liquid to a solid, and at 100 degrees Celsius, water transitions from a liquid to a gas. If we increase the pressure to about 1.5 atmospheres, then it turns out that the solid-liquid transition still occurs at around 0 degrees Celsius. It doesn't change very much, but the liquid-gas transition occurs at a higher temperature. It's at about 112 degrees Celsius. Whereas in turn, if we lower the pressure, so if we went down to about, say, 3/4 of an atmosphere, then again the liquid-solid temperature stays about the same, but the liquid-gas transition temperature decreases to about 92 degrees Celsius. So one can make plots like this, that is, these little one-dimensional plots at lots of different pressures. And scientists like to organize this in what we call a two-dimensional phase diagram. So this is a phase diagram where on the x-axis we have the temperature, and on the y-axis we have the pressure. And what we do is we label the locus of points where the material changes from a solid to a liquid to a gas by simply connecting the dots of the lines that we've just drawn before. And this is something that we call a phase diagram. So this is a two-dimensional phase diagram, and you see in this phase diagram that there is a region, there's a big region where the material is a solid, there's another region where the material is a liquid, and there's a third region where the material is a gas. At any point that you are on the phase diagram, so you can always find out what the behavior of the material is. So, at 1 atmosphere and about 23 degrees Celsius, you can read off this plot that water is a liquid. But this allows you to generalize it to many other conditions. Let's try to use this plot for a minute to cook something, just notionally. So imagine that you wanted to cook a perfect egg. So we've talked about cooking perfect eggs before, and we'll talk about them again, you can be sure. But, the problem that we told you before with cooking a perfect egg is that if you boil water at 1 atmosphere, the temperature is 100 degrees Celsius, and that temperature is well above the temperature, about 64 degrees, that you would use to make a perfect egg. But the reason that we use that as our target is because in the absence of other equipment or ideas, then boiling water is an easy transition to identify, and thus we know that if we put the egg in when the water is boiling, we know that at least it's hot enough to cook the egg. So how could you make this work? So this is what I would recommend. Actually, I'm not sure I would recommend this, but this is one way that you could do this. So what you should do is you should climb a mountain. And you should climb a tall mountain. So if you climb a tall mountain, and the mountain is at exactly the right height, so that the pressure on the top of the mountain happens to have a boiling point, which we can read off the phase diagram as 64 degrees, then when you boil the water on top of that mountain, you will cook a perfect egg. And so if you look at the phase diagram of water, which we can do right about here, then it turns out that that corresponds to a pressure of about 25 kilopascals. It's about a quarter of atmospheric pressure. And that actually, it turns out, has a boiling point temperature at about 64 degrees. So that is a strategy to cook a perfect egg. But I should tell you there's one problem with that strategy. So you could ask, what temperature would an egg cook if you cooked it on the top of Mount Everest? So it turns out that on Mount Everest, the boiling point of water is such that it's about 71 degrees Celsius. It's actually a bit higher than that of a perfect egg, just because the atmosphere is a bit too dense. And so you would actually have to find a mountain higher than Mount Everest to cook a perfect egg at the boiling point of water. And I wish you luck with that. Now, chefs, not wanting to climb mountains to cook perfect eggs, instead have various pieces of equipment that they use to manipulate the phase diagrams. And I want to just go through a couple of them right now. So one piece of equipment is called a pressure cooker. And this actually is used to increase the pressure in the kitchen. So a pressure cooker looks like this. And basically what it does is it raises the pressure in the environment at which something is being cooked. And thus, according to the phase diagram, causes the boiling point to actually increase. Now, typical pressure cookers have settings that basically allow the pressure to go up by about another atmosphere. So the pressure in the pressure cooker is about 2 atmospheres. And it turns out that the temperature that corresponds to, again, just reading off the phase diagram, is about 120 degrees Celsius. That, of course, accelerates cooking. That makes cooking happen much faster. To see how that works, and just to sort of admire how much faster it can occur, what I'm going to show you right here is a recipe for cooking potatoes. So usually if you cook potatoes in boiling water, I don't know about how you all feel about this, but I always think that it takes forever. I mean, you have to put the water in, then you have to wait for the potatoes to cook. And you have to wait really, I mean, I don't have very much patience, but it takes quite a long time. On the other hand, if you look at this recipe for cooking potatoes in the high temperature, the high pressure setting of a pressure cooker, which, as I said before, is about 2 atmospheres, then the potatoes, it says, cook in about 4 minutes. And the reason that it's so accelerated is because the high pressures cause higher temperatures, and the higher temperatures just cause the relevant phase transitions within the potato to be hit much more quickly. So this is one piece of equipment that chefs use to manipulate phase diagrams. Another piece of equipment we discussed actually last week, or Dave Arnold discussed last week when he was talking about cooking the perfect egg, and this is called an immersion heater. An immersion heater is a machine that basically allows you to cook an egg or any other piece of food at a temperature that you dial in with a knob. It contains a motor element that literally controls the temperature of the water bath to be whatever you want. And this, of course, is very powerful because it allows you to sit wherever you want on the phase diagram of water and not be so dependent on the boiling point for your phase transitions or for your cooking to occur. So the final piece of apparatus that I'd like to discuss, that we will discuss also further in this class, is called the rotovap. And the rotovap, that's a short name of rotary evaporator, and that actually operates by lowering the pressure that you're cooking something in. So, for example, a rotary evaporator can take something and lower the pressure by, say, 25%. And when you do that, then we've already discussed the boiling temperature goes down, which means that it will take longer for things to cook. But it's also a much more gentle way to actually cook food. And for that reason, you will see that many of our chefs use it to great end. The last thing that we want to do in this section is to return to the phase diagrams of carbon dioxide and nitrogen, which we discussed before. I showed you the temperature dependence of the phase diagrams for those two materials at 1 atmosphere. And I want to show you the phase diagrams in their full glory when you do it as a function of pressure. And so let's just start out with the mystery that we had last time, which was that of carbon dioxide. And this is the phase diagram for carbon dioxide as a function of temperature and pressure. And what you see is that whereas at 1 atmosphere of pressure, there's a solid phase that's next to a gas phase, so there's a solid gas transition. If you go up to higher pressures, there is actually a liquid phase. So around 8 atmospheres, there's a very clear liquid phase. And so there's a critical temperature where the material will transition from a solid to a liquid, and another temperature where it transitions from a liquid to a gas, just like that we saw in water. And so we can demonstrate that again just in a one-dimensional phase diagram. So at around minus 54 degrees, carbon dioxide at 8 atmospheres transitions from a solid to a liquid, and at around 46 degrees, it transitions from a liquid to a gas. And that's actually, so in fact, the carbon dioxide, the behavior of carbon dioxide doesn't look so different than that of water as long as you look at it in the right pressure range. So this is something that we can actually test in the laboratory by doing an experiment. And now we're going to show you a demo by the great Daniel Rosenberg, who will demonstrate that actually carbon dioxide does indeed become a liquid if you increase the pressure enough.
Here is dry ice. Dry ice is carbon dioxide that is at minus 80 degrees Celsius, so that it's frozen and a solid. Dry ice cannot exist as a liquid at atmospheric pressure. It goes directly from a solid to a gas, which is why it's called dry ice. There's no liquid involved. But if we raise the pressure, we can put the dry ice, we can put the carbon dioxide in a place where it can exist as a liquid. And the way we're going to do that is we're going to take a few little pieces of dry ice and put them in a microcentrifuge vial and going to seal it up so that the gas cannot escape. Because the gas can't escape, the pressure inside of the tube is going to go up. When the pressure inside of the tube reaches about 5 atmospheres, the dry ice reaches a point where instead of going directly to gas, subliming, it can melt. It can turn from a solid to a liquid. Now what's going on right now is heat going into the tube is causing the dry ice to sublime. As the gas builds up inside of the tube, the pressure goes up. And as the pressure goes up, there it goes, the dry ice now can melt. So what we see in there is liquid carbon dioxide with a couple of pieces of solid carbon dioxide, which we can't really call dry ice at this point, floating around in it. Now it's actually pretty important to release the pressure before all of the solid is gone, because this is a phase change. Once the solid is gone, the pressure starts to rise again. So I'm putting a little bit of safety on this, giving it a chance to vent. Now we have mostly liquid, and if I release the pressure, the liquid carbon dioxide can no longer exist as a liquid. And because it's still cold, it condenses straight back into a solid.